Thank you. It's lovely to be here. I can tell my mic is working, so I'm just going to keep going. So yeah, the purpose of my talk is basically to set up David for his, and we will go through some of the basic notions in causal inference and causality. And the broad theme of this intro will be to sort of conclude that the usual statistical language that we use in learning is not sufficient to talk about causal concepts and causal queries. And so in a lot of different fields of science, we're interested in learning from some observations that we make how to better perform some kind of action that we're interested in. It might be, for example, in a medical setting that we are very inspired by or in work on in our group, we're interested in how should we best treat the patients that come to our hospitals. But you can also think about public policy questions. How should we tax a certain product to get people to essentially avoid using it if we think it's harmful? Or how should we tax our population so that we get the right distribution of wealth if we have some interest like that? But there are also tons of private policies that we might be interested in. For example, if we want to increase the sales of some product, if we're a company selling a product, we might consider having a sale to boost the sales of that product, or perhaps run an advertising campaign in order to get people to buy more. And we might be interested in how should we best perform that campaign in order to maximize profit. So these types of policy questions appear almost everywhere. And to reason about the effects of such policies, we also need to reason about causality, because essentially what we care about is the impact or the effect of the intervention that we do to the system. So I will start by saying that there are a lot of questions like this that has a causal component. We will mostly be talking about three types of questions today. And they will broadly be categorized as hypothetical questions, which might be, if I have a patient that comes to my hospital today, what if I treat this person a certain way? What will happen? And this is kind of a looking forward perspective.
Can you write just a little bit bigger?
Oh, yep, absolutely. And another type of question which is very related, but kind of retrospective, is a counterfactual question. I'm going to write. Is this better?
Yes.
Okay, cool. And this asks, what would have happened if I did something different? And an example of that might be, say I have a headache, right? And I take an aspirin to treat my headache. I could ask retrospectively, what would have happened if I didn't take that aspirin? Would I still have a headache, or would I be fine anyway? And the last kind of question that we might be interested in that has a causal component is an explanation type question. So essentially saying, okay, I started a company, and after 2 years, my business failed. What was the reason for that, for my business failing? And all of these questions are asking about the cause of something, or the effect of some cause. And we will see in many examples why statistics is not, the classical statistical language is not sufficient to talk about these types of questions. So I'll start by giving an example. Well, first I should say, actually, the goals for today, are to describe such languages that can answer that type, or describe those kinds of questions. And attempt to answer them. And we'll cover some standard solutions for trying to answer mostly hypothetical questions. We won't go so much into the explanation side of things. It depends on what you consider explanation, I suppose. But I'll make that clear in a bit. So, where does this appear? Well, one example that I saw a causality researcher give, that was Jonas Peter, who's now in Copenhagen, is the following. Say that you observe the expression or the activity of some gene in some organism. Let's call that activity of gene X. Oops. and you're interested in how this gene relates to some phenotype that you care about. So this might be, for example, a disease of this organism or something else. But let's assume that this phenotype is somehow undesirable. So you would like to get rid of it somehow, perhaps. And then you measure this gene in organisms and the activity of it, and you measure its relation to this phenotype, and you might see some data in whatever way, okay? So if this is some phenomenon that you would like to limit, you might consider what happens if I knock out this gene, right? What if I go in artificially and set the activity of this gene to 0? What will happen? So if you look at this statistically, this looks very nice and linear, and it seems like, well, this is trend going, so we might project that, well, perhaps somewhere in this region is where the activity, the phenotype will be if we knock out this gene. But this is only valid, this is a valid extrapolation only under some assumptions. So for example, if we believe that X actually causes, this gene X actually causes Y, then it's very reasonable to assume that the activity of this, or the phenotype Y, will go down as we knock out this gene. That's very reasonable to assume because that's essentially how this plot was created too. This gene varied somehow, and as a cause of that, the phenotype changed as well. But if we believe that another explanation is possible, which is that there's a third gene, or a second gene rather, Z, which causes both X and Y. So X and Y are correlated, but they're only correlated because of this gene Z, then perhaps the following prediction is more reasonable. We believe that if we knock out the gene, the phenotype will be somewhere in this range, because actually what we do to X shouldn't affect the phenotype Y. So these two scenarios are very different fundamentally, but unfortunately, as I'm sure many of you know, the language of statistics is not necessarily, it's not sufficient to separate the two. And so this is kind of the purpose for looking at causality as its own kind of language, or that's why we need additional terminology to describe these situations. So another way to think about that is that if we observe some system that we're interested in this case, we observe X and Y, two variables, and we get some observations from that system. We can't really say anything about the causal impact or the causal effects within that system without actually disentangling what the system is. We need some notion of how the mechanisms work in order to make causal conclusions. So we can't really treat that system as a black box anymore. Okay. So the first point that I would like to make is that we need to sort of distinguish statistical and causal models. And in statistical models, what you care about, the quantity that you ultimately want to get is the joint distribution of the variables in your system. So you want this joint distribution P of x, y. In this case, we have two variables. If you have more, you want the joint of all of them. But in statistical learning, typically you want to learn P of x, y given some data, right? So you're given a bunch of samples. And you want to infer, or learn rather, this distribution. And then what you use that for is typically some kind of prediction problem, perhaps, or you might go into just analyzing properties of this P. And it's not this is not a trivial problem by any means. Learning this function, or learning this distribution P of xy is, as you know, it's a hard problem in itself. And a very easy way to see that is to consider what I'm sure you've seen a lot of times before in your life, this fitting a curve to some data, right? So we observe some samples like this, and we're tasked to fit a curve to these data points. I hope you can see these little dots here. I'm sorry about that. And there are many lines that fit, or many curves rather, that fit this data, right? And in order to, a good learning algorithm, or a good model for this P should be one that predicts new data well, typically, one that generalizes. So if I pick a line like this, it fits the data very well, but it's unlikely that it will predict well for a new point. That's the typical argument that we make in statistics or in machine learning. So learning P of xy is hard in its own, and it's hard because the inverse of going from a set of samples to the distribution that you started with is, this inverse problem is ill-posed. There are many different inverses that are possible. But the point that I would like to make is that the causal problem is even worse, in a sense, because not only do we need to infer what is the distribution, or learn rather, what is the distribution of the variables involved, but we also have to learn what is the causal relationship between variables. And that's additionally an ill-posed inverse problem, because there are many possible ways things could be causally related. So instead of just predicting for a new point, say that I observe a new point x prime here. In statistics, I need to predict, or in machine learning typically, I need to predict where would the y be for this point x prime. But in our kind of scenario, in the causal questions that we want to ask, we need also to predict the effects of an intervention, where we go in and knock out the activity of some gene, or we go in and set this x to a certain value, right? And we need to predict what happens under that in those types of scenarios. And this is different because if you think about a system such as the altitude of a city, right? And its relation to temperature, say, in that city. So we know that these are related somehow physically. The temperature goes down as we go up. And they are related, say, that the distribution of cities is governed by some P of x, and the temperature given that location or altitude of that city is described by some mechanism P of y given x. Now, these the joint distribution of these two variables could be decomposed like this. We could have a multiplication here between these two, and that would equal the joint, right? But it could all equally be decomposed in P of x given y and P of y. These are equal by definition, and there's no way for us to tell from data which one is the correct one without making further assumptions. So this hints at the first problem of inferring causal relationships, and that's directionality. We can't really tell which of these causal directions is the right one, but as we know both from intuition and from physics, we don't expect if we raise the temperature of a city for the city to rise into the air, right? Or rather, if we lower the temperature, I suppose. So we know that there's something going on here, right? One of these directions is more causally sound than the other. So the second issue that I would like to raise is that of confounding. And that's the scenario of the second example that I gave, or the first example that I gave, rather, where there's this gene Z that affects both the first gene that we talked about, X, and the phenotype Y. So we can draw that in the following way. We have a gene Z that affects a gene X and the phenotype Y. Okay? So the problem for us here with confounding is that if we observe some correlation between these two variables, we can't rule out the presence or sorry, the existence of some unmeasured variable z unless we also measure z. It's just observing this correlation is not enough for us to conclude causation, and I'm sure you've heard that in a lot of different ways. So I think all of this has motivated the need for a causal language for you. And we will go through now the first of two languages that I will be using to describe the types of queries that we want to make and the types of solutions that we might be interested in. So I'll make an attempt at this board cleaning here. I've been told that, oh, yeah. That works very well.
You just have to give it a second to dry.
Okay, thanks. So the first framework that we will be talking about is something called structural causal models. And I've kind of hinted at it already by drawing arrows between variables over here. And the way I kind of glossed over what I mean by this arrow, and I'm sure you've seen them in other contexts before, maybe as a Bayesian network, a probabilistic model. But what we'll, and when we go to causal land, we will prescribe a different meaning to these arrows, which is one of causation. So we'll see how that turns out. Okay. But the first point I would like to make is that we have this concept of an intervention. We go in and we knock out a gene, or we go to a hospital and we treat a patient, or we start running an ad campaign. And these things are different from just observing. So doing is different from observing because we don't let the sort of don't let the system proceed as it would have normally. And the reason why that is special is because then statistics don't cover statistics doesn't cover that type of event where we perturb the system. So the first concept that we will introduce now is the concept of the do calculus. And this was introduced as a way to distinguish between an intervention and a conditioning on some event. And the way it's written is the following. So the probability of a variable y after intervening on x will be written probability of y given do, and then some perturbation of this x, or some intervention on that x. And this is not in general equal to the event of conditioning on this variable. And a very easy way to see that is the example that we had before. This is exactly the scenario of the altitude and temperature. So as we said before, if I were to intervene on temperature and raise the temperature of a city, I don't expect the altitude to go up. But if I change the altitude magically, I expect the temperature to change, right? But on the other hand, if I observe, if I condition on, let me see. So let's call this y and x. If I condition on the temperature being low, that tells me something about where the city is, right? So if I observe a very unusually low temperature, that says that probably the city is high up. So the conditioning tells me something, right? But intervening on temperature shouldn't tell me anything. If I set the temperature to be a certain degree, that shouldn't tell me anything about where this city is, okay? And that's why these things are different. Yep?
Is it true that when you intervene on the causal thing, they will be?
Yes, exactly. So if I intervene on this side instead, all right, so in this case, this is actually true in this example, but in the general case, it's not. But as you say, if I intervene in the causal direction, these could be equal, yeah. Exactly. Okay, so this is one type of intervention where you go in and set the value of some variable to a certain value. But there are other kinds of interventions we might consider too. And one interesting special case is where we change the distribution of x to be something else. And this will be important later, where we think about performing randomized control trials. And what we do there is that we set the distribution of treatment to be random. And I'll explain what I mean later. But for all intents and purposes, you can think about that as a patient. We collect a group of, say, 1,000 patients, and we randomly assign them to be either treated or not treated. And you can think of that as an intervention where we change the distribution of treatment from what we observe in data or in a hospital normally to something that we control. OK. So as you hinted at, or with your question, there are times where these two quantities are the same. And a handy way of seeing when that happens is to take the graphical view that I started presenting a little bit over there. So structural causal models are called so because they have a, they're associated with a causal graph, as we say. So a causal graph is like a probabilistic graphical model in the sense that it's like a Bayesian network, I should say, in that it has a directed acyclic graph. So that means a DAG, which means that nodes are connected with directed edges, and there are no cycles. So there can't be a scenario like this. This is not allowed. And what
it's not allowed because it makes the math hard as opposed to it's not.
Good question. So in this specific framework, it's not allowed because exactly what you say. Like the math doesn't work out, and the reason it doesn't work out is because you can cause yourself in that scenario, and there are ways to treat that. So what people might do is what you call unrolling the graph. You might cause a future version of yourself to be different, right? So if I take an action today, it will probably impact me as a person later. But typically, then you would separate that into different time steps. Yep.
Is there an implication that time is going in the direction of the arrows?
Well, in some sense, yes, in that we don't expect causation in the reverse order of time. But I won't be talking about time here today, if that answers your question. Yeah. But as you kind of hinted at with your question, an arrow will indicate causation. So two nodes in this graph, let's call them U and V, for example. U causes V if U is an ancestor. Can you see this, by the way? Is this too low? OK. I'll go up here. U causes V if U is an ancestor of V. I'll make that a bit bigger. So if I'm somehow earlier in a path of some variable, I'm an ancestor of that variable, and that means I'm also a cause of that variable. We call it a direct cause. So U is a direct cause of W if there's a link between them, a direct link between them. So if U, V connected, and connected in this directed fashion. So what this allows you to do, having this graph associated with the variables, is that it allows you to very easily reason about the difference between these two quantities. So if we have two variables, U and V, the way we should understand an intervention like this is that we remove any influence of a variable set of parents from that variable. So if we were to intervene on V here, if we go in and set that V to some value, there's no way any other variable will affect that, right? If we have multiple things influencing this V, if we go and manually set that V to be something, these no longer have an effect variable. So what is typically done is that you consider instead the truncated graph, where you remove any incoming edges. Or maybe I should do this instead. You remove any incoming edges to illustrate the event that you've intervened on V. So what you also can see then is if you intervene on V and these edges go away, V doesn't tell us anything about U and W anymore. Yep?
Is there a way of working in an intervention on, for example, here U and V?
Yes. So we're allowed to do that too. We're allowed to do condition on do V equals V and do U equals U, etc. If that's what you're asking.
I see. And I see. The assumption is that the relationship between U and V doesn't matter because you managed to set both of them. So
exactly. Yeah. Yeah. And this is kind of specific to atomic interventions where I remove any information about U and W. Where in the case where I generalize and set it to some distribution, I might just change the effect of these. And these that could be captured in a related but slightly different framework, which is called structural equation models, where you describe your system using a set of equations, one for each variable, telling you how it is determined by its parents. And essentially what an intervention is then is to change that equation. I'm not going to have time to go through that in detail, but yeah. All right. So this graphical view, I think, is very useful for its generality. We can describe many kinds of scenarios using it, and specifically we can reason about many different kinds of interventions, as I mentioned before. Another cool thing about the graphical framework is that it makes clear a concept that is called mediation in a way that other frameworks don't. So if we have three variables again, U and W and V, and we're interested only in the effect U has on V through W. Let me see if I can come up with an example of that. So if we, this is tough. I should have thought of this before. But anyway, U will have some causal effect on V, both as a direct cause, and through its effect on W. And we might be interested only in the effect it has through W in some case. So if we have if we make a change in public policy, we might be interested in how it affects through changed lifestyle choices or something like that. Yeah.
How about living in a city and then you can like inhale pollution, or you know on lifespan or something?
Yeah.
You can inhale pollution and that can affect your lifespan, or you can have lots of other things about living in a city that affect your lifespan.
Good point. Yeah. Yeah. Exactly. Yeah, that's perfect. So, that's I think what's cool about the graphical framework or the causal graph framework, because it makes very clear that you can reason about these things. Because what you consider then is the effect through some path in the network. That would be a mediated effect. But in a lot of cases, the generality is unnecessary. There are tons of causal questions that we could ask that all have a very similar form. And in fact, it's exactly this kind of form. I'll change notation because we will need that later. But a very common scenario in science is that we have some specific intervention that we care about. Let's think about the treatment of a patient, right? So we have some treatment T, and we're interested in its effect on a specific variable. Let's call that Y. And we can think of this as the outcome of some of the treatment of a patient, right? So, for example, it could be the blood pressure of a patient, or it could be the survival of a patient after a surgery, or a quantity like that. And we're interested in what is the effect of the treatment that we want to assign to this patient, and both on average, but also for a specific patient, what would this treatment do to a single individual? I'll try and remember to do this a bit Okay. Now, this is a typical setup of a randomized control trial. You have some treatment that you consider. You flip a coin to determine who gets the treatment and who gets the placebo or the alternative medication, and you measure the outcome. And that's all you need to do, essentially. But in a lot of cases, this is not possible. For example, if you want to know what is the effect of smoking on lung cancer or the risk of getting lung cancer, you can't typically flip a coin to determine who smokes or not. It's unethical. And in a lot of cases, it's also impossible, not in the smoking case, but in other examples, it's impossible to randomize treatment. So another quantity that we will need is some context. And it will be clear later why this context is important. But this could be something that describes a patient, for example. It's his or her health record, or if I'm running an ad campaign, this might be the previous sales of some product or the previous sales entirely on a marketplace. And that could be used, that could be itself determine what would be the outcome of the experiment that I would run. But it also could affect what treatment is prescribed normally. So think of this again as the health record of a patient. That is likely, that would likely impact which treatment they receive in the future. So if we observe data from a hospital, this is a very convenient way to think about it. We observe some treatments and we observe some context and we observe some outcomes, and we would still like to be able to ask questions like, what will the effect of treatment have on this patient? Okay, so this type of setup appears, as I said, in many different contexts, and it can be conveniently expressed in a language which is kind of complementary to the graphical language. And this will be the second sort of framework that we discuss, and it's called the potential outcomes framework. And in the causal world, these are still somewhat separated. People usually prefer one or the other. But I think it's, some scenarios or some settings call for one and some call for the other. And it's useful to know about both, I'd say. So in the potential outcomes framework, instead of drawing a graph and using do notation, we will reason about this specific scenario over there. It's slightly more general than what I've drawn there, but let's for now consider only that case. So the potential outcomes framework is so named because we reason about potential outcomes. And a potential outcome is essentially representing what would have happened under some treatment. So y parenthesis t would be what would have happened if I intervened with t. So again, think about that as the outcome of some intervention or treatment on a patient. And we will focus now for a while on the binary case, treat or don't treat, or medication A versus medication B, or a medication versus a placebo, for example. So let's say that, t is in 0, 1. That means we have y0, and we have y1. And this will be the control outcome, as we say. And this will be the treated outcome, or the outcome under treatment. And so the key question, or the key thing to realize here, and which makes it different from statistics, is that we can only observe one of these, typically. We can only either treat a patient or not treat the patient. We can't do both. So if we were given the choice, which of these would be better, that question is now a causal one. We would have to reason about what would have happened if I didn't do the thing that I elected to do, right? So another way to see that is to say that the outcome that we do see, let's call that y again, is, can be written like this. So if we treat, t will be 1, and we will observe y1. And if we don't treat, t will be 0, so this will be 1 minus t. and we will observe y0. So in some sense, this is an assumption called consistency, which says that if we treat according to t, we will observe the potential outcome of that treatment. So whether you think that's reasonable or not, it depends on the settings, I suppose. So for example, if we give a patient a treatment and they don't take it, then we don't actually observe the potential outcomes that we would hope. But there's other ways of handling that. So we will assume that this is the case for now. And a typical quantity that we are interested in is what's called the treatment effect. And the treatment effect is simply the difference between these two. And there are two kinds that we will talk about today. The first one being the average treatment effect. Or the ATE. Is also sometimes known as the population average treatment effect, which is simply the expected difference between these two quantities, y1 and y0, over the population that we're studying. So we can put p here for population if we would like. So the way you should think about this is essentially, on average, how much better is it to use treatment 1 than treatment 0? We will talk a little bit about how to estimate this quantity. Then there's a conditional version. Oops. And it's called the conditional average treatment effect, so I'll just write conditional 8, which is abbreviated CATE. And CATE is then the effect of an intervention conditioned on some set of attributes. And you'll see now why I put the context x there, because what we will be interested in is the conditional effect when conditioning on this x. So think of this as, for a patient with a specific health record, what will be the effect of choosing one treatment over the other? Sorry, I see that some people are reaching out up there or struggling to see, so I'll write it up here too. And the reason we might be interested in this quantity, the CATE, is in order to personalize treatment. So this average treatment effect basically says, okay, how much better on average is this treatment than the alternative? And it allows us to say, should we treat everyone with this or should we not? But it doesn't allow us to say, for a specific individual, which will be the better choice. So for that, we need something like the conditional average treatment effect, which allows us to be more granular or more fine-grained in our policy. Okay, and the larger x here, or the more descriptive x here is of a patient, the more individualized we can make the treatment, but also the harder it is for us to estimate it. Like you have fewer and fewer patients that look the same in terms of x. Okay, so I have a few minutes left, and I'll end by giving you an example of why the average treatment effect is not so straightforward to estimate, and how we could do it anyway. So there's a famous example of a study of kidney stone treatment in which two treatments were compared, treatment A and treatment B. And it was found that in 78% of cases, treatment A was successful, and in 83% of cases, treatment B was successful. So it appears that somehow treatment B is better than treatment A, right? So on average, it's more successful. Yep. Observational, or? We'll get to that. Yes. So this was observational in the sense that it was observed of patients coming to a hospital and they were treated somehow, and we observed these two numbers. But what the analysts then did was to divide these numbers up and say that for patients with small stones, so this is somehow measuring the severity of the condition, with small kidney stones versus large stones, the story was quite different. So it was observed that, 93% of patients with small stones had a successful, for them, treatment A was successful, and 87 for treatment B, and then 73 here, and 69 here. So in both of these subgroups, it appears that treatment A is better than treatment B, but not on average. So who can say what happened here?
You gave treatment B more often for the small stone.
Exactly, yes. So there are more people in this group than in that one, and there are more people in this group than in that one. So another way to say that is, well, you gave treatment A to sicker patients on average than you did treatment B. So of course it's going to be harder to get a success, right? So this is an example of this, where the context or the confounder, in this case, was the size of the stone. The size of the stone both determined the treatment, but of course also affects the probability of success or the outcome. So what this tells us is that, well, this here would be the expected outcome under some, or conditioned on some treatment, right? So we can write this as the expected y conditioned on treatment being 0. I'll use that instead of A. And this would be the expected outcome given t equals 1. Okay? And these two, I think I need to erase a little bit more. The difference between these two will not be the average treatment effect in general. So the expected difference between y t equals 1 minus is not the same as the expected potential outcome minus the expected potential outcome under control. And the reason is confounding. So there are essentially 3 different ways of tackling this that are common. The first one is randomization. And in randomization, what you do is that you, as we said before, if you have the size of the kidney stone, we don't want that to affect treatment because that will confound our results, right? So what you do is instead you randomly assign treatment to patients so that it's independent of the size. So that's one way of getting around this, because then under randomization, basically the conditional will be equal to the potential outcome. Another way, which is popular, is adjustment. And that's essentially what the researchers did here, and there's a few more steps involved. But it's to adjust for any confounding that exists. So if the size of the stone is a confounder, it affects both the treatment and the outcome. Adjusting for that in your analysis will give you an unbiased estimator of the average treatment effect. And the way that you do that is quite, once you know it, is quite easy to realize why that makes sense. So yeah, I have time to go through that, right? A minute or two, okay. I'll just say also that reweighting is a third option that is commonly done. And what is done there is to weight people that look like the opposite treatment group higher. So essentially, I don't think we will have time to go through this, but this is the area of propensity score methods that you might have heard about. And the goal there is to make people who receive treatment B appear to be the whole population. And people that then appear to be drawn from the other treatment group are weighted higher, and in that way you can reweight your sample so that it looks like it came from the original whole population and not just the treatment group. So in adjustment methods, I will end on this note because that's related to what David will be talking about in his part. And as I mentioned, the goal is to adjust for the confounding that's present in the data. And it relies on a few assumptions. And the one that I'll mention is ignorability. So essentially we say that it's possible for us to identify or estimate in an unbiased way the average treatment effect if the following thing holds. The potential outcome, yt, is conditionally independent of the treatment given the covariates x, or the context x. And the way you should read this is to say, no matter what treatment I actually got, what would have happened under any treatment is kind of independent of the thing that I did get, right? If I were to undergo surgery, the result would be the same regardless if I got surgery or not. Okay? So under that assumption, when this is conditional on x, so this kind of takes away the variation of the individual, we can note that the expectation of this potential outcome that we need in order to construct our average treatment effect estimate, conditional on x, I can write this as yt conditional on x and t because of this assumption here. I can just add t in the conditioning because it doesn't matter. But now, since I know that t, oops, I should say t equals t. Since I know that t equals t, this thing here would just be y. Because we had before that y equals t times y1 plus 1 minus t y0. So if I keep going here, I can say that this is the same as y, conditional on x and t. So this is now the observation that we had. And it's kind of leading us towards this, right? We still have an x to get rid of. But that we can do simply by taking the expectation of this quantity over x. So that means that if we do expectation of y given x, t, and this outer expectation is over x, we will have the expectation of yt given, of yt under these assumptions. So this hints at a way of estimating average treatment effect in practice. This thing here, you should think about as a regression. Y is given by some covariate x, and we fit a function, or we fit some type of curve to predict y based on x and t. So you can think about having one line for the treatment group and one for the control group. And then you take the average estimates of those regression over your whole population, and that will give you an estimate of the potential outcome that you get. Okay, this last part was a little bit rushed, but this is known as the adjustment formula. And this is a general technique that you can use. If you believe that you have measured all relevant covariates for predicting both the outcome and the treatment, then this condition, ignorability, will hold, and you can use this technique to estimate both average treatment effects and conditional treatment effects. I will end there and take any questions you have.
So I've been following this seminar series for a couple of years now as a silent participant, watching all of the seminars online, and we're really excited about what you're setting out to do here at the Broad. And as was just mentioned, I'm a new faculty member here at MIT. I'm part of the Institute for Medical Engineering and Science, the Computer Science and AI Lab, and Electrical Engineering and Computer Science. And I'm also a member of the Broad as of this year. So the problem that my research really is motivated by is that of healthcare. Here in the United States, we see cost of healthcare growing dramatically. We see adults having often multiple comorbidities, which are diagnosed late or often inappropriately managed, and as a result of these can often have complications that might have otherwise been prevented. Now, at the same time, we are at a really interesting place in terms of data, because since 2008, the adoption of electronic health records in the United States has grown dramatically, from 9.4% to well over 84% today. And as part of the data that's being collected as part of just the practice of medicine, we see both unstructured data coming from clinical notes written by clinicians. We have imaging data continuous vital signs taken for patients who are hospitalized and increasingly also at home, laboratory test results, data that we don't typically think of as being part of the electronic health record, but are increasingly so, such as proteomics and genomics data, and data that we don't even necessarily think about as healthcare data, like social media or mobility information gathered from your mobile phone. And this data gives us a picture of what is going on with a person's health. And it's a picture which we can increasingly try to take advantage of to try to address those challenges I just mentioned a minute ago. Now, the second major change, in addition to having data, is that there have been a number of breakthroughs in machine learning in the last 10 years, we'll say. So in the media, you hear a lot about our advances in computer vision, where what I'm showing here is the ImageNet benchmark data set for object recognition. And we see on the y-axis, we're looking at measure performance. We want it, or error, we want it to be as low as possible. This red line is human level. And this was 2011, it's roughly 25% error rates. Over the years, as advances in deep learning got better and better, the performance improved until today. We're at well over human accuracy for this specific problem. And the same trends we've seen time and time again in other areas as well. In speech recognition, for example, you get this plot. Here we're looking from 1993 up to today. Y-axis, again, is some notion of error rate. In this case, it's what's called word error rate, the fraction of words that are understood of what were spoken. And notice that this y-axis is on log scale. Okay? So down here is really, really small. And across a number of different benchmarks, you can look at how the performance has increased over time to today. We're again getting close to human accuracy for this specific type of problem. So of course, not all of us focus just on object recognition or speech recognition, and many of the people in the room today are motivated by problems of human health and disease. And so there's been a lot of excitement about bringing these techniques from AI into healthcare, taking advantage of the type of data that we have now available. And we've seen in the press other types of excitement. So there was a lot of coverage of this article written by the Google team on diagnosis of diabetic retinopathy. There was a lot of press on this article written by a group of folks at Stanford on looking at X-ray images and trying to diagnose a range of phenomena such as pneumonia. And there was a lot of press on this article written also by a Stanford group on doing dermatologist-level classification of skin disorders. But does that mean that AI is going to be changing all of healthcare tomorrow? Is this just the cusp of what is going to be coming in the next couple of years? Well, I hope the answer is yes with regards to that second question. But throughout the next few minutes, I want to motivate to you that these problems, as important as they are only a very small fraction of the types of clinical questions that we need to deal with. And these successes are not necessarily representative of the challenges that we're going to be confronted when we tackle other clinical questions. Specifically, these problems are diagnosis problems, and they only require prediction. Let's look at a few other questions and see how prediction might not be enough for those challenges. Here's an image of a woman's breast. This woman has breast cancer. And we might want to know, based on this and other data that we have on the individual, what is the likelihood that this patient with breast cancer will survive 5 years? Now, predictions of that nature could be really valuable for staging patients to understand how aggressive is their disease. Do we need to initiate treatment now? Or, for example, imagine this was a prostate cancer where where there's been a lot of attention now to this question of should we be treating or should we just be waiting? To answer each of these questions requires an understanding of what is currently going on with the individual, what is their progression going to be like. But importantly, progression
has to be well defined. So let's think about, if we were to not do a careful definition here, how we would try to think about solving this problem using a machine learning tool. So, for example, we could try to train to predict survival and then use that to guide patient care for new patients. So we create a data set. Data set has patients with these imaging coming from the time of, let's say, first diagnosis. And from this data set of, let's say, a few 100,000 women over the last 10 years, we look to see how long each one of them lived. And of course, hopefully a lot of them are still alive, so this will be a censored data set. Some of them will have died. And then we could attempt to use straightforward predictive modeling tools, such as a survival modeling, to predict what is the survival time for each individual given this data that we have. What could go wrong with that approach? Any ideas? Yep.
Treatments change, the landscape is changing. You're predicting something that depends on a situation that will no longer.
So the answer that was given is that treatments change. And so this model of predicting survival implicitly depends on the current treatment landscape. And as we develop new treatments, people might be able to survive longer. But I want to break down the first word of your response, which was treatment. Did the word treatment show up in anything that I said here, other than need to know when to initiate treatment? Notice that almost all of these patients with breast cancer were treated, period. They were treated. And so if we're going to predict survival for these patients, what we're going to be looking at, the data that we have is going to look a little bit like this. And so this is a bad example. This should probably not say David, but perhaps a woman. So there's the moment of diagnosis. We're going to call the data that we have for them X. This is the input for our predictive model. And we want to predict something about survival, let's say 5-year survival, which we'll call an outcome Y. Right? Suppose we have this data on a few 100,000 women. We attempt to learn a model to predict Y from X. Well, suppose the model that you learn on a new, then for a new person says this person is going to survive another 30 years. If all the clinical team does is look at that prediction, they might conclude, oh, okay, we don't need to treat this individual because they're going to survive a really long time. But the problem here is that inside this data was treatment. Right? So what happened between diagnosis and outcome was the patient's disease might have progressed, and at some point they received treatment. And it was because of that treatment that they might have, or might be because of that treatment that they survived. And so we might be, if we were to just naively use this predictive model and say, don't treat this individual, we might be killing people because we wouldn't be initiating treatment where we should have been initiating treatment. Is the problem clear? Here's a second example. So here's an example of of a new type of pathology, which is getting dramatically more data on patients than existing types of pathology would do. And we could ask, well, given this new information we have on a patient, what treatment would work best for this individual? Right? So it's not how long would they survive, but really now we want to try to guide treatment decisions. And the motivation for this is that people respond differently to treatment, as Fredrik discussed quite a bit in his primer. So we could attempt to use electronic health record data, use data from other patients and their journeys to try to guide these future treatment decisions. For example, we could attempt to learn a simple predictive model to look at past individuals, what data was available for them at the time of needing to make a treatment decision, and predict what treatment decision was made by the clinical team. And then maybe use that to guide future treatment decisions. Again, straightforward machine learning task, right? What could go wrong there? Someone else. Yeah.
So we want the opportunity to make better decisions now that we have better data, but you've only talked about previously available types of data and trying to replicate the decisions that were made in the past.
Good. So, so you're going a couple steps ahead as was previously done, and you're saying, well, this would never work if we now have new treatments, first of all, because we wouldn't be able to, or either new treatments or new data, right? Because we have no examples of them in the past. But let's suppose we did have examples of them in the past.
I think more fundamentally, the problem is that if people made bad decisions in medicine before, and we're just going to learn the outcomes of bad decisions.
That's exactly the point that I was hoping to make right here, which is that the best this could hope to do is to mimic existing medical practice. And medical practice today, for some problems, might not be very good. Right? For some tasks, and I'll give an example later today of guiding choice of second-line diabetic therapies, maybe currently we are flipping a coin to decide what therapy to use because we simply don't know. And so if you simply take data of this sort, where we have some individuals, we have the treatments that were done, if the treatment that was chosen is flipping a coin, it's completely random, it's independent of what we know about the individual, then we will learn nothing from trying to mimic predicting the treatment. And so that's yet another problem. And of course, our hope is that from doing this learning, we will be able to improve medical practice. And so here as well, we need to change the question we're asking. So we have to formalize this problem now of individual, treatment, and outcome, and ask something about the causal effect of the treatment on the outcome, given what you know about the individual. I'll give you one last example. How do we optimally manage patients with sepsis? Sepsis is caused by an infection. If left untreated, the immune system's response to the infection can lead to organ failure and ultimately death in many cases. But there have been a number of studies showing that if you apply a policy, and one widely studied policy is known as early goal-directed therapy, then you can dramatically reduce the mortality rates for patients with sepsis. And this policy is an algorithm. It says, well, start out by giving antibiotics, measure their central venous pressure. If it's less than something, give them some fluids. Maybe we'll do some, maybe at some point you need to give some pressors. Measure some other things, and iterate. And this is a policy that's being applied over and over and over again until some goals are achieved. But we might want to ask the question of, well, this is a policy, but how do we know it's the optimal policy? Maybe we can use data gathered, for example, from critical care units to try to come up with a better policy altogether. Now, of course, if everyone only ever applied this policy, we would be hopeless. Right, for many of the reasons that Fredrik argued you need to think about when doing causal inference. We need some variability in the data, and luckily people don't perfectly apply this policy, and so there is a lot of variability in the data. And so one could try to formulate this as an off-policy reinforcement learning problem, where one takes this data over time and attempts to optimize a sequential policy in order to achieve the highest final reward. And this goes by many names. Off-policy reinforcement learning is one commonly used in AI, but in the medical community, it goes by the name of learning dynamic treatment regimes. But the point I want to make here is that it's important that we recognize that this is only as it's at least as hard as a causal inference problem. And the way to see that is as follows. Suppose that this was not a policy, but a one-time action, right? So there was a single point in time where you have to decide, make this treatment or don't make this treatment, or make treatment A or do treatment B, right? If we were trying to optimize that choice, it's just like the problems I showed you in the previous slide. And so under the hood in doing off-policy reinforcement learning is a very hard causal inference problem from observational data. And it's only harder because you have to do that repeatedly over time in order to learn an optimal dynamic policy. And so if you don't pay attention to the fact that this is a causal inference problem, if you were to just, for example, take the off-the-shelf tools that have been used for playing the game of Go or Atari, that have been getting a lot of press lately, applied that to this healthcare scenario, and you could, and there have been recent papers trying to do so, and then get a policy out and say, okay, I'm going to just apply this policy now to new patients, you could kill people if you do not pay careful attention to the assumptions needed to make valid causal inferences. And this is a major failing of the community, which we're not paying attention to what those assumptions are. We're not thinking about what are the checks and balances we need, what is possible to statistically derive from the data that we actually have. And we need to be paying attention to those questions. All right, so I hope I've motivated you that causal inference shows up in many different places where we want to apply AI into healthcare. But the last thing I want to do is to tell you a little bit about clinical data. It's messy. It's really messy. Right? So here's my data across time. We might have some genetic data, maybe taken at one point in time. We might get repeated blood test results, a lot more blood test results and monitoring when I'm hospitalized. We have very incomplete observations about me. Only when I see a healthcare provider do I get detailed data, and even then, it's often as unstructured clinical notes written by doctors. So it's difficult, right? So every single step of the causal inference pipeline, whether it be figuring out how to derive treatments and outcomes from the data, to whether it be thinking about how do we condition on patient data, which is as heterogeneous and lives in such multiple timescales, each of these are really hard problems. And they make that causal inference task only more difficult. So in the remainder of my talk today, I'll tell you about two methodologies that my lab has been building to take a first step towards solving some of these hard causal inference problems that I mentioned. The first piece of the talk will be about formalizing that problem that Fredrik discussed of causal inference from observational data, formalizing it with math in a way that we can hope to really understand what are the assumptions needed in order to make valid causal inferences, what can we provably say about the causal effects that we can infer, and really understand how do we design machine learning algorithms if your goal is causal inference. And that'll be for a one-time point question, given at this point in time, figure out what is the best treatment to make. But as I was just motivating over the last few minutes, there's often a sequential question, and patient data comes over time. Often we have treatment across time. And so the second part of today's talk will introduce a new methodology that we call deep Markov models, which are applicable to many areas of science, but we think are particularly well suited to tackle these problems in healthcare as well. So here's the story that we'll discuss first, which is causal inference of treatment effects. The picture is as follows. We have the following causal graph, which I'm assuming is the known causal graph. We have some information about the patient. There's some treatment, T, and we're trying to ask something about the effect of the treatment on the patient's health, which I'm going to call Y. Now, critically important, here I'm assuming I know the directionality. So for example, we don't wonder whether the health causes the medication or the medication causes the health. We assume that we know the directionality here. But what we don't know is the strength of the edge. And we don't know also anything about the heterogeneity of the effect. For example, which are the patients for whom giving the intervention has a positive effect. That's what we want to infer from data. And a good example of this, which has, for example, been studied recently by Dmitry Bertsimis here at MIT, is to understand what second-line treatments should we give to patients to control their diabetes, where one could attempt to ask and answer these questions using observational data. So remember, the variables here are x, t, and y. Let's be a bit more specific. So the patient history might be what we know about Anna on May 15th. We know her age, gender, race, blood pressure, white blood cell count, temperature, and we see that her blood sugar is high, and a whole bunch of other things. And what we want to figure out is, well, what would be the effect of giving her treatment 0 or treatment 1? Treatment 0 you can think about as the control treatment, treatment 1 being the one that you're studying. We'll call that the treated population. Now, as Fredrik pointed out, you can formalize this using the language of potential outcomes. And so y_0, y0, is the potential outcome of what would be Anna's blood sugar in September if we gave her treatment 0. And y1 is the potential outcome of what would be Anna's blood sugar in September if we gave her treatment 1. Now, of course, we don't observe both of these. In the data, she only got one of the treatments at that point in time, and so we observed either y0 or y1. But in order to figure out how to act optimally for Anna, we would like to be able to predict both y0 and y1, and then use that to guide the treatment decision. So for example, if y0 is less than y1, we would say give her treatment 0. So our goal will be to try to learn how to infer these potential outcomes for new individuals by using data that was previously collected as part of the practice of medicine, what I'll call observational data. And the challenge is that that data may have been biased by patient-doctor preferences and many, many other factors. Formally, what we want to do is predict what's called the conditional average treatment effect, or CATE. I'm going to denote that as tau of x. X is the input, what we know about Anna in May. And what we want to predict is the expected value of y1 given x minus the expected value of y0 given x. And if this is positive, then we take one action. If it's negative, we take another action. Now, the key challenge is that we can't just learn tau of x directly from data because we never observe it or even a noisy sample of it in the data itself because the data only ever has y1 or y0, never shows you the difference between them. So that'll be the methodological direction which we will be formalizing, and Fredrik mentioned several approaches, several classical approaches for thinking about how to do that estimation. Now, just to point out that if you could estimate this conditional average treatment effect, then you could also immediately get the average treatment effect just by averaging these values over individuals x. So in my talk today, I will be making a very strong assumption. And it's this assumption which is going to be required to say anything formally about our algorithms. Loosely speaking, that assumption is of no hidden confounders. So if there were any confounding factors which affected both which treatments were given to these past patients and the outcomes themselves, then we assume that they're somewhere recorded in our data. Of course, our data is high dimensional, so it may not be easy to find those confounding factors and to correct for them, but they should be in our data somewhere. And that's going to be an assumption that we're making here. So we can formalize this conditional average treatment effect estimation problem using machine learning by assuming that we have data, x, t, and y, drawn from some underlying distribution, which I'll call p. Our goal is to learn functions of x and t where that function is approximately equal to the expected value of the potential outcome yt given x. Right? And if we had these functions f, then we could estimate tau of x by just computing f of x evaluated at treatment 1 minus f of x evaluated at treatment 0. And that'll give us our estimate of CATE, of the conditional average treatment effect. So, okay, we have a candidate approach. This approach goes by the name of regression or response service modeling, if you're familiar with the causal inference literature. And roughly speaking, what you would do is an empirical risk minimization. You take some loss function, you look at the, you add up your loss function over your training data, or you look at your expected loss with your empirical expectation. So for example, if your loss function were a quadratic loss or squared loss, then your objective function might be looking at a sum over your training data of f of xt minus yt. And critically, we're only looking at the YTs that were actually observed in the data. And we then try to find an F that minimizes this empirical risk. And in doing so, we get our F out, which we could then use for future individuals to estimate Kate. But there are a lot of unanswered questions here. For example, what objective functions should we be using for learning if we knew that we would be using your Fs later for causal inference in the way I've been saying? Right here, I gave you one candidate learning objective, which is just empirical risk minimization. But is that the right learning objective? Maybe we need to rethink the way we do machine learning if we know we're going to be doing causal inference down the line. So what should the losses be? How should we regularize learning? And if we're thinking about function classes like deep neural networks, what types of architectures can we expect to work well for these causal inference problems? So these are three of the questions which I'm going to give a first answer to right now. So the key challenge which arises in observational settings is that of model misspecification and finite data. So consider for now, in fact, consider for the next 10 minutes, that we're only going to seek to estimate f of x comma 1, right? So we only want to estimate the effect under treatment y1. And then obviously, if you just repeat everything I'm going to say for y0, then you have what you need to estimate your Kate. But this will allow me to write to simplify my diagrams. So let's look at the following picture. Here we have a single covariate or feature, which is the individual's age across time, controls age across this x-axis. We're going to look at how the potential outcome y1 behaves as a function of individual age, and this red line is the ground truth. Now, these red points are samples from the conditional distribution of x given t equals 1. So these are individuals who were treated. And these blue points are from the control group. They're individuals who were not treated. They were given t equals 0. And because I'm not assuming that this came from a randomized control trial, p of x given t equals 1 might be different from p of x given t equals 0, because there was some bias in the way that treatments were assigned during in the training data. Right? So these two distributions are different. And what happens then is if you try to use a straightforward machine learning algorithm, keep in mind that the only y1s we actually observe are these red points for individuals where the treatment was given, t equals 1. These blue points, we never observe the corresponding y1 because for those individuals, the treatment was not given. So for example, if you were to fit a linear model here, this is what you would get out. And you see that it gets pretty good predictive accuracy on the individuals that receive the treatment, but it gets really bad predictive accuracy on the individuals who didn't receive the treatment. And so if you're to then use this for classification later, you would notice that this actually gives very bad estimates. In particular, it's very over-optimistic. It thinks it's doing really well when it's not doing well because of the fact that there's this other distribution, the one it needs to generalize to, that it doesn't generalize well to. And just to be clear, this happens because when we're doing causal inference, we are working with what's called distributional shift. We train using one distribution, which is the individuals who are treated, and we need to be able to generalize to a different distribution, which are the individuals who weren't treated. So there's a standard approach to try to fix this, which is just inverse propensity reweighting. So we're going to now change our objective function. Rather than just doing typical empirical risk minimization, we're going to reweight each data point by the probability that that data point was treated divided by the probability, that it was not treated, divided by the probability that it was treated. Right, so we could attempt to use machine learning to learn a model of treatment decisions from the past, so past treatment decisions, and then use that to try to correct for this imbalance in some way. So the picture would look a little bit like this, where this data point out here, where it's really the sole individual that was treated who is old. But because we know that in the training data, there are going to be a lot of individuals that are old who they were not treated, but we know that they exist. we're going to upweight that individual's data point, and in thus doing so, put more weight onto that regime of the space, and what we get out is this model, which is no longer over-optimistic. Now, the challenge with that approach of using propensity scores to do reweighting is that these propensities, probability of treatment given X, are rarely known. In some settings, like in web search settings where advertisements are being shown, you might actually know the policy that was used to show the advertisements. But of course, in the healthcare setting, we typically don't know the policy. Now, one could say, well, let's learn this from data as well, and then attempt to use that to do the reweighting. But that too has problems. For example, we can't really say anything about its statistical properties with finite data. What happens if we don't estimate it very well? How does it affect the results? Even if we do know it perfectly, it turns out that those estimators I just showed you aren't very good estimators because they can have very high variance due to one of the denominator probabilities being very low. So there are a number of problems with this standard approach, and what we'll attempt to do is give some theory which will suggest a new algorithmic framework. And that theory is based on a generalization error bound that Fredrik and a former postdoc of mine, Shalit, had come up with. This generalization bound roughly is as follows. On the left-hand side is the counterfactual loss. This is the expectation with respect to the individuals who did not receive the treatment of the prediction error were we to give them the treatment. Okay? To be clear, we never observe this. We cannot estimate this in our data, so we can't optimize it. But what we can observe is this term on the right-hand side, which is the expectation with respect to the individuals who did receive the treatment of the error of our predictions were we to give them the treatment. That we can estimate. And what we're going to do here is we're going to reweight those losses just as we did previously, but rather than using a ratio of propensities, we're just going to plug in a function, W1 of X. And that's going to be a weighting function. And of course, if W1 of X is equal to that ratio, then this will result in exactly the same thing. But W1 of X could be something else. Now, what this bound shows is that if you were to add the second term in, which is an imbalance between reweighted groups, then these two terms together, adding them up, actually provides an upper bound on the counterfactual loss, the thing which we can never actually compute. So what is this balance term? Well, it uses what's known as an integral probability metric, which you should think about just as a distance function between distributions. If you were to ignore W1x here, this is looking at the distance between the distribution of people who did not receive the treatment to the people who did receive the treatment. If this came from a randomized control trial, that distance would be 0. Of course, it didn't come from a randomized control trial, and so it's not going to be 0, but we now have a free parameter here, which is this weighting function that we can use to try to make them look closer to one another. And that weighting function then shows up in both our distance and our new distance between the reweighted distribution, and it shows up in this reweighted loss function. And these two things together, it's shown in our work, actually provides an upper bound on the counterfactual loss. And so this now provides a first answer to many of these challenges we just saw. We can now do learning by minimizing this right-hand side, all of which consists of terms that we can compute using our data. What it ends up looking like is a learning problem, which now, instead of just minimizing over functions f, also minimizes over these weighting functions W1 of x. The first term here is this reweighted regression, and the second term here is this distance measure between distributions, and this plays a role in guiding us to learn good weighting functions. And critically, this bound applies for almost any weighting function. It has to satisfy a minor constraint about it being a valid reweighting, sort of the expectation with respect to, basically we need to make sure that this is still a distribution. That's the key idea. But other than that, this will always give you a valid upper bound. And so this now allows us to think about the statistical properties of being able to estimate this from finite data And we will be able to think about using weighting functions which are not necessarily very complex, but which allow us to estimate it accurately and trade off between the accuracy of the bound and our ability to estimate it from data, or the tightness of the bound and our ability to estimate it from data. Now, there are a couple of twists that arise and ways that we can make this a bit better, which I'm going to go through relatively quickly in order to make sure I have enough time for the second half of my talk. So the first challenge that arises is that notice that here we're measuring the distance between two distributions. And as many of us know, measuring the distances between anything in high dimensions is very hard. And so when x is high dimensional, and if we had finite data, then estimating that term on the right-hand side is going to be quite hard. We need a lot of data to estimate it well. But a key insight that we had is that your data often lives on a manifold. So consider this data that lives on this manifold. It's a bit hard to see, but this is what it looks like. Suppose that our treatment and control groups looked a bit like this, where red is individuals who were treated, blue are individuals that were not treated, the control group. Now, if you look at these two samples up here, these two samples are close in Euclidean distance, but you would not want this data point to, you would not want to think about that as the representative sample for this untreated data point, because they're very far from one another under the underlying manifold. And so if you were to just naively, if you were to ignore the manifold and naively do the reweighting approach, you would get something like this out, where this data point is upweighted to stand in for this one, and this one is upweighted to stand in for all of these. Of course, as you get infinite data, this problem no longer arises under some of the assumptions we gave, because you'll eventually see some red points here and some blue points here. This problem really arises when trying to estimate these distances in the finite data regime. But the insight we have is that we could also attempt to simultaneously learn the manifold while learning these reweightings. And if you were to take into consideration the manifold, then what you hope that your algorithm will result in is this type of reweighting shown here, which will give much better performance in the finite data regime. So we're going to use representation learning to learn the right metric. That'll be the second key idea here. So finally, our algorithmic framework is as follows. We're going to use what's known as a treatment agnostic representation, which we came up with and is particularly well suited to deep neural network approaches to causal inference. We're going to use a flexible outcome model. I'll show you what that means in the next slide. And we're going to use imbalance minimization, where we're going to attempt to regularize our learning objective to encourage this reweighted distribution to be close to the treated distribution. So the basic architecture that we suggest using is as follows. We have the input, what we know about the individual, or their context, shown here as x. We're going to push that through a few layers of a deep neural network to get a common representation out, which we'll call phi. And then, so the way that this function x comma t is going to be parameterized is that we're going to have two heads. So if, to predict t equals 0, or said differently, to predict the potential outcome y0, we're going to take this representation and feed it through a few more layers of a deep neural network to predict y0. But to predict y1, we use a different head of the neural network, which goes this route. And then, of course, in your data, you observe either y0 or y1 for each individual, and you can measure the loss, L, with respect to the corresponding observed potential outcome, where you only use the corresponding path for that prediction. Now, this uses a shared representation, phi, for predicting both y0 and y1, as opposed to, for example, having independent functions to predict y0 and y1 with no shared representation, or as opposed to, for example, giving the treatment in over here. Notice the treatment is only showing up really over here. Now, if you take this basic idea and now put it together with the theoretical results I just showed you, we get reweighted counterfactual regression, what we're calling RCFR. So I'm just going to expand the picture a little bit. Yep?
What is the intuition behind having this use the shared representation?
I'll give it to you in a second. So we're going to expand this picture just a second. And what we're adding now is this weighting function, w of x, which is going to be a function of the, you could either have it be a function of the context X or of the shared representation. That bit doesn't matter. But then our objective function is going to now change. Rather than just minimizing the empirical risk or the unweighted loss, we're going to minimize the weighted loss where the treatment decision, where this weighting function is then used to reweight the losses, as I showed you earlier. In addition, we're going to add in this new regularization term, this imbalance term, which is going to look at the imbalance, the distance between distributions between the reweighted individuals who did not receive the treatment and the reweighted individuals who did receive the treatment. But critically, it's now going to be evaluated in this phi space, okay? And this is the answer to your question. The reason why we have this shared representation is because it gives us that manifold I was talking about a few minutes ago. And we're going to be measuring distance now not in X space, but in phi space. It gives us a common space. And so that solves that second problem. And what we show in our work is that this learning objective actually minimizes an upper bound on the conditional average treatment effect, the thing we actually care about. If you don't mind, I'm going to hold questions until there's going to be a Q&A session afterwards. I just want to make sure I get through my talk. So evaluating causal inference is very challenging because you typically don't have data where you have both the outcome and the opposite outcome for each individual. We used a widely used benchmark called derived from the Infant Health Development Program, IHDP, where it was a randomized study that looked at the effect of home visits and high-quality childcare on child cognitive test scores. The feature set included aspects of the child, the mother, the pregnancy, and so on. And this was turned into an observational data set by removing a subset of individuals, which induces a bias in the treatment. But because the original data came from a randomized control trial, it's possible to actually get an unbiased estimate of any policy that was used based on any policy that was inferred based on an estimated Kate. So what I'm showing you here are results on this benchmark data set comparing a variety of different algorithms. On the very top are the standard approaches that are used widely in the causal inference community. For example, using ordinary least squares, with two different functions, one for treated, one for not treated, using k-nearest neighbors, a doubly robust method such as targeted maximum likelihood estimation, Bayesian additive regression trees by Chipman et al., causal forests, which is a recent work by Susan Athey and her collaborators, and which is specifically aimed at trying to address this problem of how do you do causal inference using machine learning. So these are several different existing approaches, and what I'm measuring for each of them is a measure of the error in estimating this tau of x, the conditional average treatment effect. That's the first column. And the second one is the error in estimating the average treatment effect, which is just obtained from averaging over the Kate. On the bottom are our methods. So TARNet does not use any of the advances that I mentioned in terms of how do you reweight the loss function, how do you regularize properly, but it does use the idea that I mentioned of using a shared representation and sort of using this particular architecture for causal inference. And that immediately gives it a big boost in performance, taking your error in predicting Kate from roughly 2.3, which is the best with BART, down to 0.95. If you were to add on to that this idea of learning the manifold, this shared representation, and penalizing your imbalance between the distributions, so learning the representation in order to minimize that balance, then those are these approaches that I'm calling CFR-MMD for using a imbalance measure called the maximum mean discrepancy, and CFR-Wasserstein for using a Wasserstein distance between distributions. And that improves your error quite a bit further from 0.95 down to 0.78. And if you were to then add in this reweighting term, so this W of x that you also learn, you get to this reweighted counterfactual regression approach, which brings down the error even further down to 0.67. So this just gives you a sense of really how these different pieces can show up in a very classical problem. But of course, the goal here is not to just do causal inference in this low-dimensional setting from this benchmark, but to actually be able to enable now doing causal inference in healthcare where you might have images as input or much more, or large gene expression arrays as input, or much more complex data. And our theory and our algorithms and our initial results all suggest that these approaches should actually perform very well in those settings. So to summarize, what I've told you so far is that I've given you the first error bound for conditional average treatment effect estimation that holds under model misspecification. It suggests how to change the learning objective when your goal is causal inference. And there are a number of ongoing directions that my lab is interested in. For example, how do you generalize to multiple treatments? How do you develop similar theory for sequential decision-making for the off-policy RL setting? How do you build algorithms to specifically identify responders, individuals who will respond to the intervention versus individuals who will not respond? And how to deal with confounding, hidden confounding, which we recently wrote a NIPS paper about. So in the remaining 4 to 6 minutes, I'm going to tell you a little bit about this last approach, learning deep Markov models. And this is really tackling some of the other causal inference challenges that I said arise in healthcare. For example, so this is a non-causal question, just trying to figure out what is the typical trajectory of a patient with a rare disease? Or asking the question about 5-year survival time. I gave the breast cancer example. You could ask it for many other settings. In the absence of any treatment, that's where the causal aspect comes in, because you're asking about something that may not have been observed in the data explicitly. Or asking about something about disease progression, or asking something about what complications might arise for patients and when. So the challenges in answering these questions from health data is that we have very noisy health data. For any one individual, we might only get data on them for, let's say, 2 to 4 years, because people are changing health systems all the time. We don't have good interoperability in the United States. And somehow, if we want to try to get a 20-year story, we have to stitch together data from across all of these different patients. And if you want to ask a question like, what would happen to me over the next 5 years if I didn't do treatment, we need to answer that from data where patients might have been getting treatment. And so those are confounding factors that somehow we need to deconvolve the effect of those treatments in order to assess something about what would happen to me if I didn't do treatment. And these are really challenging problems. So the approach that we've been developing attempts to use, you could think of it as analogous to this regression setting, but now having a time-varying model and bringing in hidden variables to take into consideration that we don't have very clean data. So we're going to learn a model of how a patient's state evolves over time and how interventions such as medication affect that patient's state. And in order to learn these models, we've developed a new learning algorithm which is very broadly applicable for learning high-dimensional nonlinear time series models. So the model is known as the deep Markov model. It was published in a recent AAAI paper by my student Rahul Krishnan and postdoc Shalit. And what the model stipulates is as follows. So to be clear, this is like a hidden Markov model, except the differences will become clear in just a second. So we assume that the patient's state is given to by these variables ZT, which vary over time. So Z1 might be May, Z2 might be April, Z3 might be September, and so on. We never observe the true patient state. We're going to assume it's some high-dimensional latent quantity, like it might live in 100-dimensional real space. What we do observe are a number of observations about the patient, which I'm going to denote as X1, X2, X3, and so on. That might come from blood and urine test results, diagnosis codes, vital signs, results of expression studies, and so on. We also assumed that there were a number of actions or interventions that were happening across time. Now I'm going to denote as these U variables. And of course, those actions depend in some way on the past patient state, because the doctor looks at the patient, they make a decision about what to do. And they also affect the future patient state. So we have these edges going from the U's to the Z's because the actions affect what happens to the patient. So if you could learn these models from data, then they provide an in silico model for assessing the effect of interventions or actions by forward sampling in the model. So given patient data up to one point in time, you could then ask, what would the future X's look like under certain settings of the interventions? And do forward sampling in this model, fixing the U's as you would like in order to assess the downstream X's. And because we are doing interventions, one would use Pearl's do calculus in order to do the corrections, where you would use what's called graph surgery and break these edges from the X's to the U's that you're intervening on. So we know that patient state evolves in a very complex manner. For example, the way that treatment might affect patient state could be highly nonlinear. And so in order to try to parameterize these models sufficiently flexibly, we're going to use deep neural networks both for the transition distribution, so taking as input the previous hidden state and the interventions to predict the next hidden state, which is again a high dimensional vector. We'll use a deep neural network for that. And we'll also use a deep neural network for the mission distributions. And in this work, we're going to be using what's called a nonlinear Gaussian state-based model. So our assumption is that ZT will be given to you by a Gaussian distribution of this nonlinear function of ZT minus 1 and UT minus 1, shown by this deep neural network, and similarly for the variance of that Gaussian. Now, this provides a very flexible, very rich model family to work with, but the challenge arises in how do we learn it from data? And so this isn't a new class of models per se. This is just another stochastic nonlinear dynamical system. And although there wasn't all that much work using deep neural networks, there were some papers, but there's tons of work in the control literature on doing learning and inference in these types of models with fixed, typically known dynamics. And in that literature, they've thought about how to learn, how to do inference, but the challenges are that here, Z, when we're trying to learn, is typically unobserved. And most of that literature assumes that Z is observed. So exactly evaluating the likelihood of the X's and computing gradients in order to learn here is very hard. Moreover, much of the previous work considered very small dimensions, both for the hidden space X and for the observation space, for the hidden space Z and for the observation space X. And so what we will show is that we could use recent advances in machine learning to dramatically speed up learning in these classes of models and make it now possible. The key idea will be to use stochastic gradient descent on a variational lower bound on the likelihood. We're going to come up with a variational approximation of the posterior P of Z given X, which, although this, by the way, here, this is a probabilistic model, turns out that we're going to be able to use some of the recent advances in learning recurrent neural networks as an inner loop in learning this probabilistic model. In particular, we'll show that this conditional distribution Z given X can be parameterized by a bidirectional recurrent neural network. The result of doing that is that we now amortize the cost of doing inference during learning. It uses, for example, 50 times less memory than traditional variational inference learning algorithms here, and overall learning runs actually orders of magnitude faster. So I'm going to skip through the technical details of how we do this, but for those in the room who are familiar with variational autoencoders, the ideas are very similar. We're going to use a variational autoencoder, now it's sequential one, in order to predict the Z's, now it's on the bottom, from the X's, which are the inputs. We will use a forward recurrent neural network in addition to a backwards recurrent neural network to parameterize the means and Gaussian and variances of the posterior Z's. And we also show the importance in our work, in this paper, we show the importance of using what's called a structured variational approximation and allowing you to get much better learning results. So to evaluate this, I'll tell you about two very simple experiments we ran. The first one is a fully synthetic setting, taking some inspiration from the IMES dataset widely used in machine learning. We created the healing IMES dataset. This is a dataset of handwritten digits who represents patients, and these patients are getting interventions all the time. So for example, the interventions are here, we're going to be rotations. So patient 4, their subtype is a 4. Sorry, patient 1, their subtype is a 4. And they're getting a rotation at this point in time. This is what they look like now. This is what they look like a month later. This is patient 2's data. And so what I'm showing you here, you should think about as the underlying ground truth, the Z's. which we don't observe. So what we do observe is much noisier data. So there might be long-range events that have nothing to do with the patient's disease state. Maybe someone gets an infection and it lasts 3 days. We're going to denote that by these white squares that show up at some random point and persist exactly 3 days. We don't ever get a clean observation of the underlying patient health. Rather, what we observe is this really noisy picture, okay, where we just add noise on top of this. So I'm going to assume now that our data looks like this. Right? This is going to be our training data. We're going to observe sequences like this, and we will also observe a number at each time step, like 0, 20, 13, minus 14, 0, 19, 16, minus 15, which refer to the number of angles of rotation that were performed at each point in time. That's the intervention. Of course, our learning algorithm doesn't actually know anything about rotations. It only gets these numbers. And the goal of the learning algorithm is to see from these noisy observations, can we learn something about the underlying dynamics? And can we learn something about how treatment affects those dynamics in order to actually understand the meaning of the interventions, in this case, rotation? So we run our learning algorithm, and you could use that to try to clean up the data by inferring the new z's, and this is what you get out. You see that it actually successfully, it learns enough about the dynamics to be able to clean up the data. Furthermore, if you were to now take as input what's shown here on the left column, so I'm going to give just a clean input now. So suppose we now have a patient, we know everything about them, and we're going to ask the model that was learned just from the noisy data, simulate forward in time under different interventions. Let's see, did the model learn the effect of those interventions? Well, here we're going to just provide, at every point in time, we're going to provide a small constant right rotation, like 3, 3, 3, 3, 3, 3, 3. This was never seen in the training data, to be clear. Neither were there ever seen clean instances, and neither were we ever seen sequences of these particular rotations. But yet the model is able to perfectly predict the effect of these interventions. Thus, it has inferred what is the meaning of the intervention. So this gives us some confidence in the approach. Next, we looked at a data set of diabetic patients, 8,000 diabetic patients, measured over 4 years. We looked at a very small number of observations on them, summarizing laboratory test results and some diagnoses that are relevant for assessing complications and progression of diabetes. And we used 200 latent dimensions for ZT. So the first thing I'm going to do is just talk about model fit. So if you're to train this learning algorithm, on the x-axis here is epochs or iterations of learning, and the y-axis I'm showing a held out log likelihood or a bound on it. What we see is first that we want this to be as high as possible. If you just use a linear model, so without using the real power of these deep neural networks in the transition and emission distribution, you can't fit this data very well. And so what you get out is this green line. If you were to, on the other hand, use a deep neural network for the transition and emission distributions, we find that you're able to much better capture the nonlinear dynamics in the system, and you're able to fit the data much better. That's that black line up there. The lines in between correspond to using either linear or nonlinear transition and emissions. Now, next we look to see, can we try to assess something about counterfactual effects for diabetes treatments? And this is motivated by that work I mentioned earlier on figuring out which second-line diabetic treatments work best for whom. Here we're going to look at a toy problem. It'll just be a sanity check. So what I'll show you in the next slide is just a result asking, can we figure out, do diabetes medications lower glucose? Just that. And we know the answer is yes. Okay? So this will be a quick sanity check. Does our algorithm do something which makes sense? Now, the way that we use this deep Markov model to answer this question, we have, as before, we have interventions which are medications, but we found it also important to not only model the medications, but also to model interventions that correspond to orders, lab orders. Because the data that you observe, for example, lab test results, are going to be affected by whether a lab test was even ordered or not. In some sense, the missing data is affected by these U's. And so by explicitly modeling those interventions as well, we will be able to change the way that we read out from this model. When we do this forward simulation that I alluded to earlier, we're going to fix the U's all to be to 1. So we're going to say, observe the lab test result at each point in time. And that'll allow us to try to look to see, for example, what is the patient's glucose in the future. Even if, for example, were you to not do that, if you were to just sample from the data without doing that intervention, then you might observe the following results at each point in time in the future: glucose not observed, glucose not observed, glucose not observed, glucose not observed. And you would never be able to infer anything about what happened to the patient. So this is a trick that we developed to be able to read out from the model. So here are the results. So the patients that we considered are all individuals who did receive diabetes medication. In particular, we aligned them all by the first time they received metformin, which is the typical first-line therapy. And for this sanity check, what we asked was the following. Given what we know about the patient up until the time of the first therapy decision, do a forward simulation under the two following worlds. World 1, where they received the diabetes medications that they actually received. We're asking about retrospective patients. And world number 2 is where they didn't receive any medications. Okay? And to be clear, we never observed that latter world in our data, never explicitly at least. So what I'm showing you here now in green are going to be the individuals, the samples across time, and we're going to look at the fraction of individuals with high glucose values. At time 0, for our current threshold of high glucose is 70%. 3 months in, if we do not give them the medication, the number of people with high glucose levels is roughly the same, right? And what our model says is that as time goes on, if you don't give them the medication, their glucose levels will rise. 3 months in, if you did give them the medication, there's these green lines, we see a dramatic drop, about 10% in this case, of the number of people with high glucose levels. And so what our model has learned, focusing specifically on that short time point, is that, well, as expected, diabetes medication causes a decrease in glucose. And this is nothing new. We, of course, know this, but it's a good sanity check that that model is doing something, at least in aggregate, like we would expect. And the next step would be to start looking at the individual level, understand which individuals respond best to particular medications. To summarize here, what I've told you about is an approach of using time series modeling, which brings together both deep learning and probabilistic approaches, together with an efficient learning algorithm. It gives you an explicit model of the effective interventions on disease progression, which has a number of applications. For example, I've already alluded to one of them, which is precision medicine, figuring out what would the effect of an intervention be so that you can optimize it. But one could also use these approaches to, for example, find similar patients by saying, okay, suppose we have a patient, we can infer their Z2 at one point in time, and then ask, who are other patients in the past who had similar latent spaces? And try to use those past patients, perhaps with a good user interface, to suggest nearest neighbors for clinicians to use when thinking about how to do care for a current patient. We could also use this to try to discover new disease subtypes. For example, by looking to see across patients how different patients respond to different interventions, estimating the counterfactuals and looking to see are there subgroups of patients who tend to respond similarly to treatment. Now, the same approach is broadly applicable to many other areas of sciences. Just to give you an example of how broadly applicable it is, I'll give you an example from outside of healthcare, which is that of modeling music. So we took a music data set where our xt's at each point of time were an 88-dimensional vector of which keys of a piano are being pressed. And here there are no interventions. It's just observational data. We learn this model without the use on this data. And then we could forward sample from this model. And let's see a little bit about what it looks like. Oops. So what I'm showing you is a sample from the learned model. It's creating new music. Okay, so that was just to really motivate that these models are pretty powerful models, and they are, this is just to inspire you to think through that there are many other applications for them beyond the ones I just mentioned to you. So this is my last slide. Where to next? So there are a number of open directions that my lab is working on to try to make these methods I just described better, to extend them to new settings. But all of the settings I've described today really focus on this simple model where the causal graph is assumed known. You have the patient history, you have a treatment, you know that the treatment affects the patient's health, and you ask, how does it affect the patient's health? Where I'm going next in my research is really starting to relax that assumption and ask, what could we do if we could also learn and reason about the causal graph itself? For example, it would enable N-of-1 studies where we want to be able to learn how to treat patients with perhaps a rare disease that we've never seen before by better understanding the underlying mechanism. Furthermore, if we can understand the underlying mechanisms better, we could then use that to figure out what are good drug targets, how can we design new treatments altogether. All of these things require really understanding the causal graph. Finally, even among questions that seem to be just about prediction, when you go out into the field and try to deploy them, there's usually an underlying causal inference question that wants to be asked. So an example is you build a model to try to predict who's going to become diabetic in the next few years. Your model, suppose you did L1 regularized logistic regression, it comes up with a set of features which are highly weighted at the end of the day. One of those features might be gastric bypass surgery with a big negative weight. When you show it to your clinical collaborators, they can ask, oh, does gastric bypass surgery reduce the likelihood of getting diabetes in the future? So they try to look at the models and they try to ask causal questions about them. But these models were not trained to do so. So what we could ask is, could we design algorithms that could actually discover interventions directly from the data, right? Think about finding features that actually can cause something nice to happen in the outcome. And to do that properly, one also has to reason about the causal graph. So I'll stop there. Thanks so much for your attendance.